On Tuesday, we watched a video from Big Bang Theory which described the Doppler effect. We also watched a couple other videos that actually showed you examples of the Doppler effect. If you remember, the definition of the Doppler effect was, this is exactly the definition that Sheldon gave in the video that we watched, and it's perfect. It is the apparent change in frequency of a wave due to the relative motion of the source and the observer. What does that mean, though? What does that really mean? Now, you can spout that off, and that's great, but do you understand what that really means? First of all, let's identify what this means, the apparent change in frequency. The apparent change in frequency means that it isn't really changing. It just appears to be changing. This is what we might hear, or this is what we might see, depending upon what kind of wave it is. But in the end, the actual frequency hasn't changed at all. Because as you know, once a wave has been made, the frequency of the wave can't change. The apparent change in frequency of a wave due to the relative motion of the source and the observer. The wave is usually sound, but it can be other waves as well. Light waves, there's a check and reflect question you're going to work on a little bit later on today that involves light waves. Okay, visible light, red, orange, yellow, green, blue, indigo, and violet, that Roy G. Biv spectrum. Due to the relative motion of the source and the observer. What do we mean by that? The relative motion means that either the source or the observer or both is moving. When you're walking and you see somebody over there across the field, you can see you're moving relative to them. Okay? Somebody else that's kind of over on the side, kind of looking at the two of you, if not looking at the outside frame of reference, might not be able to tell who's moving. They can see that you're moving relative to one another, but they can't necessarily tell that you're moving and the other person isn't. Relative motion is just motion with regard to each other. So maybe one's moving, maybe the other's moving, maybe you're both moving, whatever. It's due to the relative motion of the source, what causes the wave, and the observer, what experiences the wave or what hears the wave. There's an equation here that looks pretty ugly. Before we actually explain that equation, I want to draw a picture here. Let's say that we've got a source of a wave right here. Yeah, that's going to produce a circular wave. It goes out in all directions. Right now, if you're in front of me, you can hear the sound that's coming from my vocal cords. But if you're behind me, you can hear the sound coming from my vocal cords as well. Essentially, the sound is going out in 360 degrees around me. Does that make sense? So what's the sound look like surrounding this point source? Whatever it is, whether it's a siren or whether it's some guy talking, the sound's going to look like this. Now, we're going to call that the first wave. Okay. Maybe a second later, that first wave that was made isn't going to be there anymore. A second later, that first wave that was made is going to be out here. Maybe another second later, that first wave isn't going to be there, but it's going to be out here. Does that make sense? Keeps getting bigger, right? The amplitude of the wave ends up getting smaller because the energy gets spread out. And that's why as you're further away from what causes the sound, you don't hear it as well, because the energy gets spread out the further it gets away from the source. But what's interesting about this is that although the wave spreads out like that, the source is moving. The source isn't there anymore. The source isn't in the middle of that. The source is right here. So now the most recent wave that was made is centered around the new location of the source. So it might look something like this. If you're standing right here, you're going to very soon experience a sound. But that sound is going to be a higher pitch than the actual frequency because the waves that you're going to experience are closer together. Once it goes past you, what are you going to see or what are you going to experience? Not these waves that are kind of scrunched up here in front of the source, but rather you're going to experience these waves that are spread apart in behind the source. So what are you going to hear then? If they're scrunched together, you hear a higher pitch. If they're spread apart, you hear a lower pitch. In other words, as the source is coming towards you, you hear a higher pitch than actually exists. As it's going away from you, you hear a lower pitch than actually exists. Remember the videos we saw? Like the fire truck going by, it sounded really, really high pitch, and then as it went by, it became a lower pitch. Right? The car horn, same deal. And this is why. It's a higher pitch because the waves are scrunched together, and it's a lower pitch because they're spread apart after they go by you. All right, there's an equation that describes this, and it's kind of an ugly one. FD is equal to VW over VW plus or minus VS times FS. Lots of S's, lots of D's, W's, V's, F's. It becomes a little bit confusing. Plus or minus, that's the worst part of it, the whole plus or minus thing. FD is going to stand for the Doppler frequency. The Doppler frequency is the apparent frequency. That's not the actual frequency. That's the perceived frequency, the frequency that you hear, if it's sound waves, that is. The frequency that you think you're hearing, as opposed to FS, which is the frequency of the source. And of course, the frequency of the source is the actual frequency, the real frequency, the frequency that's actually being produced, which doesn't really change, but appears to change. VW, VS. VS, a lot of people look at that and say, oh, VS, that's easy. That's the speed of the sound, right? Well, we're not necessarily talking about sound. We're talking about waves. And usually it ends up being sound, but not always. This equation is valid whether it's sound or not. VS doesn't stand for the speed of sound. It stands for the speed of the source. And we're typically going to measure that in meters per second. How fast the source is moving either toward or away from you. And finally, VW is the speed of the wave. And typically, the speed of the wave will be the speed of sound, because usually we're dealing with sound. All right, keep those straight, not so bad, right? Except that whole plus or minus thing. Does that bother anybody, the whole plus or minus thing? It does me. The only other equation that I can think of with a plus or minus is that quadratic equation. If you've learned it in math class, remember negative b plus or minus b squared minus 4ac over 2a, remember that? Yeah, you don't need to know that for physics, but there is a plus or a minus in there. When you're doing the quadratic equation, you always do both, but not at the same time. You do negative b plus square root of b squared minus 4ac, and then you do negative b minus the square root of b squared minus 4ac. You calculate them both. Gives you the zeros of the parabola. Here we're not going to do both, plus and minus. We're going to do one or the other. But we have to decide which one we want to do. And the context of the problem determines which one we're going to do. And you know what? I'm going to be 100% honest with you, just like I was when I was talking about that diffraction and size of the opening and the frequency of that. Remember I said, hey, listen, I'm not going to remember this. Hey, I've taught this a million times. I don't remember. Okay, frequency, how does it affect the amount of diffraction? I got to figure it out every time. Same deal here. I never remember, is it a plus or a minus when it's coming towards us, when it's going away from us? I got to figure it out every time. Here's how I figure it out. Let's assume for a second that the source is coming towards me. If it's coming towards me, then FD has got to become bigger, right? I know this. I remember this because I've watched videos. I've seen the Doppler effect. I've heard the Doppler effect. I don't have any trouble remembering that one. As the source is coming towards me, the Doppler frequency, the apparent frequency, is going to be higher. Now, here's the crux of it. If FD is going to be higher, then this bottom number here, VW plus or minus VS, has to be what? Bigger or smaller? Smaller. If you want the top number to be bigger, then this has got to be smaller. How do you get that smaller? By adding or subtracting? Subtracting. Good. If the source is coming towards the observer, we want to make that bottom sign a subtraction sign, VW minus VS. If the source is going away from us, it's gone past us already and it's going away from us, the Doppler frequency, the apparent frequency, is going to be lower. than the actual frequency. If you want a smaller number for FD, then you want this bottom number to be, Zach, you're going to want it to be bigger in that case. And if you want it to be bigger, you're going to have to add. Got it? Subtract when it's going towards you, add when it's going away from you. Don't memorize that. Okay, figure that out. You memorize that, you'll probably remember it for tomorrow. If you memorize that Sunday night, you'll probably memorize it, you'll probably remember it for Monday, for Monday's test. But then you'll have to study it again come final exam time. Figure it out. Just do what I just did, and then you don't have to remember anything. Right? All right, let's take a look at a question here. Appears on page 832. It starts off with kind of a tricky one, actually. It's not a simple, straightforward one like we usually see first. It says a train is traveling at a speed of 30 meters per second. Its whistle generates a sound wave with a frequency of 224 hertz. You're standing beside the tracks as the train passes by you with its whistle blowing. What change in frequency do we hear as it goes past us? The speed of sound is 330. So we're not looking for the apparent frequency as it comes towards us or as it goes away from us. We're looking for the change in apparent frequency. What are you going to do this? How do you find delta F? The change in apparent frequency. Michael? Yep. And then subtract it. Good. So you got the frequency of the train, the apparent frequency of the train coming towards you, the apparent frequency as it goes away from you, then you're going to subtract the two. Let's write down some givens here, guys, okay? We have train, the speed of the source is 30 meters per second. We've got a frequency of the source of 224. That's the actual frequency of the train. We got a speed of sound. We're going to say that's VW. The speed of the wave is 330 meters per second. Let's say when the train is coming towards me, my equation becomes FD is equal to VW over VW plus or minus again. Remember what it was? Yeah, minus, good, minus. Because in the end, we want that number on the bottom to be smaller in order to make FD bigger, right? Okay, let's get that value. I'm just going to say VW, 330, divided by 330 minus 30 times 224. You get 246.4 hertz. That seem reasonable? Hey, the actual frequency was 224. What do we perceive it to be here now? 246 because it's coming towards us. Seems reasonable. All right, let's figure out what it is coming away from us now. This time it's going to be VW plus VS. So we're going to say 330 divided by 360 this time, press equals, and then multiply that by 224. We end up getting 205.3. Now, if we want to find, that should make sense too, right? It's going to be a lower pitch than the actual pitch as it's going away from us. We want to find the change in frequency. We're just going to subtract those two now. 205.3 minus 246.4. Change in frequency was a drop of 41.1 hertz. That's okay? Okay, let's have a look at the practice problems on 432. Notice there's 4 answers here. I've only given you the first 2 questions, so if you're looking in your book for this as opposed to up on the board, don't do the last 2. Just do the first 2 questions, okay? All right, everyone, let's take a look at question number 2. It says, an airplane is approaching you at a speed of 360 kilometers per hour. I'm going to circle that kilometers per hour. So regardless of what variable that is, I know I'm going to want to convert that to meters per second. Now, the pitch, you measure the pitch of its approaching engines to be 512 hertz. We want to know the actual frequency of the sound that the sound needs to be if the speed of sound in air is 345 meters per second at that temperature. we're going to convert that to meters per second, but, you know, if we had the speed of sound measured in kilometers per hour, you could actually get away with using kilometers per hour. Can anybody explain to me, based on the equation, FD is equal to VW over VW plus or minus VS? Can anybody explain to me why you could get away with using kilometers per hour as long as you were consistent in the problem and get the same answer? Yep. Yeah, if the other speed was in kilometers per hour, what would happen? What could you do? If this is kilometers per hour, this is kilometers per hour, and this is kilometers per hour, it appears in every term there, it could cancel, right? So it doesn't matter whether it's kilometers per hour or meters per second. My suggestion would be just go meters per second, because we almost always have to go meters per second. There's the odd time when we can get away with leaving it as kilometers per hour, but you know what? That's probably just going to lead to confusion. Okay. In the end, if they're both kilometers per hour, you can do that, however. All right, what do we got given to us here? The airplane is approaching us at 360 kilometers per hour. That means that we're going to say VS, the speed of the source, is 360 kilometers per hour. How do you convert that to meters per second? Yep. Good. You want to times that by 1,000 to get 360,000 meters, and then divide it by 3,600 seconds to get seconds. And when you do that, I think you get 100 meters per second. So basically, we're talking about one football field per second, which, depending upon the airplane, can be typical or can be kind of slow. Actually, some airplanes move as much as 800-900 kilometers per hour. All right, so that's VS. What else we got here? We got a frequency here that is 512 hertz. Can anybody tell me whether that's going to be FS or FD? This one or this one? John? It's going to be FD, the Doppler frequency. That's the frequency that we perceive, the frequency that we hear, right? The apparent frequency. Speed of sound in air, that's going to be VS, is 300, look, I made the mistake that I told you guys not to make. Okay, VW, the speed of the wave, not the speed of sound, or not the speed of the source, is 345 meters per second. The only thing left here is to determine whether we're dealing with a positive or a negative on the bottom in the denominator there. What is it? VW plus VS, or is it VW minus VS? Tom? VW minus VS, right? You don't have to remember that. Okay, figure it out. Okay, if you want FD to be bigger, and you do because this plane is approaching, you're getting closer, you want the frequency to appear higher, then you need the number on the bottom to be smaller, and the only way to get that is to subtract them. All right. We also want to calculate FS as opposed to FD, but let's do the rearranging of that. We could treat this VW over VW minus VS as one term, so it becomes FD over VW minus VS equals whatever. So what do we got here? 512 divided by 345 divided by 345 minus VS of 100. So, boy, it looks a little ugly here. But if you do in steps, it's not so bad. Let's say 345 minus 100 is 245. 345 divided by 245 is 1.408. We'll say 512 divided by that gives me 363. Should be 364, right? Yeah, they're right. Is that a reasonable number? What was the perceived frequency, the apparent frequency? 512. Should we expect to get a lower or a higher frequency? Should we expect our actual frequency to be lower or higher? We should expect our perceived frequency to be higher, right? So our actual frequency should be lower, right? Now, would we expect it to be that much lower? Well, I don't know. It's hard to know, but in the end, it's going fast, right? It's 100 meters per second, so it's probably going to be quite a bit lower. Go ahead.
Does this matter? Like, if it's going faster, would the perceived frequency be lower?
Yes. Not slower, but yeah, no, I know what you mean, though. Yeah, no, good question. Nick said, basically, and I'm going to paraphrase your question. Please stop me if I make a mistake in what you meant by that. But Nick said basically, does it matter if it's going to go faster, if the source is going faster, we know that it's going to, I think Nick's saying, we know that as it's coming towards me, it's going to seem like a higher frequency. It's going to be a higher apparent frequency. But does it matter really how fast the plane's going? If it's going towards me, it's going to be a higher pitch. If it's going towards me even faster, is it going to be an even higher pitch? Was that your question? The answer is yes, absolutely. Okay, the speed of it absolutely does matter. If you go back to that first diagram that we drew here, back here, okay, the faster the source is going right here, the closer these waves get together, the more scrunched up they get. And if they get more scrunched up, then of course you're going to hear them quicker, 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 quicker. So it's going to be a higher pitch that you end up here. And on the other side, it's going to be a lower pitch, right? Good. Hey, what would happen? What would happen? Here's a good question. What would happen if you went faster than the speed of sound? Here, look, we're going pretty fast here, but the sound waves are still going faster because you can see the sound waves are going out away from that, right? Out away from the source. But what if the source is outrunning the wave itself? What's it going to look like? Let's try drawing that, actually. Here's my source. Okay, here's the first wave that it makes, and then a few seconds later, that wave is bigger. A few seconds later, that wave is even bigger. Well, now the source isn't there anymore. Now the source is over here. It's producing another wave that's going like this. Hey, wait, it gets bigger still. The source goes over here. Okay, produces another wave. The source still isn't outrunning the wave, right? The source is still going smaller than the wave. The wave is beating the source. But if the source ends up beating the wave, here's my first one, okay? The source is moving to the right, but as the source is moving to the right, the wave is trying to catch up to it. So you end up seeing something like this. And so on. You end up seeing this cone of waves that trails the source. That kind of makes sense? Okay, the source is outrunning the waves. Actually, that's not quite true. What you can see is this, right? The source would be in front of all the waves. That make sense? If you're standing right here on the ground or even in the air, you're going to hear a higher pitch as this plane, let's say, is coming towards you. As it goes by you, you're going to hear a lower pitch because the waves are more spread out. What are you going to hear right here as the plane is coming towards you? When the plane is traveling faster than the speed of sound. Yeah. Good. As the plane is coming towards you, you wouldn't hear anything. The only way you're going to hear something here is after the plane has gone by you. What do you hear after the plane goes by you? You hear boom. It's what we call a sonic boom. Okay. All of the crests of all of these waves interfere with each other. You know what interference is, right? Constructively to produce a big wave right here and a big wave right here. And as that flies by you, you hear nothing, you hear nothing, you hear nothing until the trailing edge of that flies by your ear and you hear boom. Somebody else is hearing a boom right now. You don't hear the boom until the trailing edge of that cone goes past you. And that's when you hear the sonic boom. Does that make sense? It's constructive interference of all these sound waves. Doesn't happen right here, right? Doesn't happen over here because you're not outrunning the sound. Here, when you're going faster than the speed of the wave, then you get that sonic boom. Yeah. What would be an example of something that causes sonic boom? Anything that travels, well, anything that generates a sound and travels faster than the speed of sound. Okay. People think like, oh, first of all, people have this misconception of when a sonic boom even happens. People think, oh, a sonic boom happens when the plane crosses the sound barrier. Okay, if the speed of sound is 340 meters per second, people think the sonic boom happens when the plane starts going 341 meters per second. Okay, that's not true. Okay, the sonic boom happens to the observer on the ground or somewhere else as the plane is moving fast in the speed of sound. So what would be an example of something that causes it? Anything that generates a sound and is moving faster than the speed of that sound, like an airplane. Now, a bullet travels faster than the speed of sound. Why do you not hear a sonic boom with a bullet? Because a bullet doesn't really generate sound, right? It fires, right? You hear a loud bang when it's been fired, but as the bullet moves, it's not generating a sound, okay? There would be this trail of a cone of air disturbed behind it, but it's not going to be any kind of boom because it's not generating a sound. Make sense? I'll give you another one that's not a sonic boom per se, but it's the exact same kind of phenomenon. We just don't call it a sonic boom. How many people go to the cabin in the summertime and go boating? Summertime at a lake, whatever. All right. Go tubing or water skiing or wakeboarding or whatever. The boat goes in the water and going slow. You're taking off out of the marina. You have to go slow until you get out to the main part of the lake, and then you go faster, right? Okay. There's no wake behind you. Okay. When you're going really, really slow. When you go faster, you don't have to go that fast to experience this, but you have to go a little bit faster than just kind of crawling along. As you go faster, all of a sudden this triangular wake appears behind the boat. You know what I'm talking about? So if this is the boat, we'll say this is the boat coming going this way. You get this triangular wake like this behind you. Why do you get that triangular wake behind you with a big wave right here and a big wave right here? Because the boat is producing not sound waves. It does produce sound waves, but clearly it's not outrunning the sound waves, right? You don't have a boat that's going faster than the speed of sound. But the boat is also producing another kind of wave besides a sound wave, a water wave. And the boat is outrunning the water wave, right? It's going faster than the water wave. So what do you get? Well, the exact same thing as the airplane produces behind it. You get this, we're not going to call it a sonic boom, but we get this constructive interference at either end, or to either side of these waves that are being produced, these water waves that are being produced like this. Right here, that constructive interference manifests itself as a loud sound. Right here, it manifests itself as a big wave. But it's the exact same thing. It's a lot easier to see here because boat doesn't have to travel very fast to exceed the speed of the wave there. Make sense? All right. We're going to have you work on a few questions for homework here. You might even finish them up in class. You got over 20 minutes here. I was going to assign for you questions 1 and 2 and then 4 to 7, but since we just talked about a sonic boom, we can do them all. Let's do questions 1 to 7. Having a look at questions 5 and 6 here, guys. It says, number 5 says, a police car siren has a frequency of 850 hertz, but you hear the siren to have a frequency that's 40 hertz greater. That means the actual frequency, Fs, is 850. The Doppler frequency is going to be 890. That means if the frequency is higher, then it means it's coming towards us. And if it's coming towards us, then what do we got on the bottom of that? That denominator is going to be a plus or minus. Minus, right? I'm just going to write that down, just so that if it becomes relevant later on, I'm going to remember that it's a minus. We want to find, we got the speed of the sound, which is the speed of the wave, 350 meters per second. We want to find the speed of the car. We want to find Vs. Now, this is a tough one. Okay, we got to rearrange this equation, and that's really the challenge with this question, right? Fd is equal to Vw over Vw minus Vs. Multiply that by Fs. Now, in order to rearrange this to solve for Vs, I want to take this bottom term, I want to put it in brackets inside the brackets, just so you recognize that I can treat it as one term here. And to get it to the top, I'm going to multiply it by both sides. So it becomes Fd times Vw minus Vs equals, well, we're left on the other side with Vw times Fs. Already it's looking better. And we still got a little ways to go before we solve for Vs here, but it's looking better already. What's the next step going to be? What are we going to get rid of next? Yep. Good. We're going to divide by Fd. So it becomes Vw minus Vs equals Vw times Fs over Fd. Looking better all the time. Let's take the Vw over now, and we're going to do that by subtracting. It's not subtracted from Vs, it's added. It's a positive number. So let's say negative Vs equals Vw times Fs over Fd minus Vw. We're almost there. We don't want to solve for negative Vs. We want to solve for Vs. So let's divide everything by a negative 1. That becomes positive Vs. This becomes negative. And the last term, negative Vw, becomes positive. There's my equation. Does that make sense, guys? Caitlin was asking me if she had rearranged it correctly, and you did. I think you did, let's say Vw minus this, I think. I think you had this term first, and then subtract this. I think so. But it's the same thing, right? It's exactly the same thing as what I have here, right? What answer should you get for Vs? I don't know. What is the answer, guys? 13.7? 15.7? Okay. Guys, I'm gonna leave you with that to solve yourself here. If you need help with that, then we'll go over that tomorrow. But now that you have the rearranging, it's probably a lot easier. See if you can plug the numbers in that and get what you need to get. Okay, I want to look at number 6 right now, and I want to finish that up before the end of class, and that's why I don't want to plug the numbers into that one right now. This says a jet traveling at a speed of Mach 1, which is the speed of sound, emits a sound wave with a frequency of 1,000 hertz. So we're going to say the frequency of the source is 1,000 hertz. We don't know what the speed of sound is, nor do we know what the speed of the airplane is, but we do know that they're the same. We know that F, or Vw, is equal to Vs in this case. What's the frequency of the sound as it moves towards you? What is it as it moves away from you? Let's deal with towards first. Let's say Fd is equal to Vw over Vw minus Vs. Let's plug in what we got here now. Vw is, we don't know. We don't know what Vw is. Vw, we don't know what Vs is. Well, you know what? We know Vs is the same as Vw. So let's do that. Why did I do that? What's Vw minus Vw? 0. So it becomes whatever Vw is over 0 times 1,000. You don't need to know what Vw is, because in the end, if you're dividing by 0, this is undefined, mathematically undefined. What does that mean in practice if it's undefined? Yep. Not 0, because 0 is inferring that there is a pitch of 0. Okay, this is undefined, which means there is no sound. You don't hear a pitch of 0. There is physically no sound. Okay, so as it's coming towards you, you don't hear anything. Now, when it goes past you, you do, but as it's approaching you, because the sound is not outrunning the source, you're not going to hear anything. Now, what about when it's going away from you? Let's deal with that. We're going to change the equation ever so slightly. Fd is equal to Vw over Vw plus Vs. We're going to say that it's Vw over Vw plus Vw, because Vs is the same as Vw. Okay, VW plus VW is 2 VW. That cancels. So I got half of frequency of the source, which is 1,000 hertz, which means it's 500 hertz. What do you hear as it's going away from you? 500 hertz. So usually when we hear that sound as the fire truck or whatever is coming towards us at a higher pitch, oh, as it goes by us, we hear that lower pitch in the transition to the lower pitch. What would we hear as it's going past us? We'd hear nothing until it hit us, and then it would all of a sudden appear as 500 hertz. Okay, we wouldn't hear that transition like we normally hear. All right? All right? Finish up those questions for homework if you haven't already. We'll take a look at them tomorrow, and then we'll spend a little bit of time reviewing for our Monday test.